Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 8. Roots of a Polynomial. Bairstow's Method. Bairstow's method is a robust tool for finding the roots of high-degree polynomials, especially when those polynomials have real coefficients, making it a valuable method for practical numerical root-finding tasks. It is one of the earliest methods for finding all real and imaginary roots of a polynomial with real coefficients. It is an iterative procedure based on the synthetic division of a polynomial by a quadratic factor, which is then used to compute its real or imaginary roots. Consider the following nth-degree polynomial with real coefficients, where a1, a2, and an are the coefficients. A polynomial may have n simple, multiple, repeated, or complex roots coexisting in conjugate pairs. Any polynomial can be expressed in terms of one of its quadratic factors as follows, where q sub n-2 is a polynomial of n-second degree, and r and s are remainders as functions of p and q. We require the solution of the following system, where p0 and q0 are the set of initial guesses and delta p and delta q are the improvements. We employ the Newton's method in section 4.8 with following substitutions, where p0 and q0 are the initial guesses and delta p and delta q are the improvements. The following 2-by-2 system of linear equations is solved within the iteration loop, where the improvements are used to estimate the current estimates of p and q. When a quadratic factor is found, the remainder should diminish. This procedure leads to the following single recurrence relationships. The method leads to the following 2-by-2 system of linear equations, where c bar sub n-1 is set to c sub n-1 minus bn-1. And solving the system using Cramer's rule, the improvements are found as follows. The iterative procedure is terminated when the sum of the absolute values of delta p and delta q is less than epsilon. As an example, consider finding all real and imaginary roots of the given fourth-degree polynomial using the Bairstow method, starting with the initial values p0 equals q0 equals 0. Also for the convergence criterion, use epsilon as 10 to the minus 5. We will start by identifying the coefficients of the polynomial as array A. First we set a sub -1 to 0. Then we take the coefficient of x to the fourth as a0 and assign the following coefficients as a1, a2, a3, and a4. We will tabulate all the results obtained in each iteration. The starting values set to 0 and 1, and the initial guesses are placed at the top of the table. For k equals 1, the recurrence relationship takes the following form. We substitute the numerical values for a1 and b0 and b sub -1. b1 is obtained as -1.3. Next, for k equals 2, this recurrence relationship takes the following form. Substituting the numerical values for a2 and b1 and b0, we find b2 as -13.4. For k equals 3, substituting the numerical values of a3, b2, and B1 into the expression for B3. We find B3 as 28.5. And finally, for k equals 4, we substitute the numerical values for A4, B3, and B2, along with P0 and Q0. We obtain B4 as minus 10.8. Now, we will calculate the array of C values, which is also described by the following recurrence relationship. The starting values for C are 0 and 1. Using B1, C0, and C sub minus 1, we find C1 minus 1.3 as follows. For k equals 2, the relationship for C2 requires B2, C1, and C0, along with P0 and Q0. Substituting their numerical values, we find C2 to be minus 13.4. For k equals 3, we substitute the numerical value of B3, B2, and B1 into the following expression, which for C3 gives 28.5. Note that C3 and B3 are available. We can calculate C bar 3, which yields 0. Now that we have the coefficients of the 2 by 2 linear system, we can solve the system for improvements, which gives minus 2.205056 and 0.805970 for delta P and delta Q. The first step estimates for P and Q are found as follows. We now repeat the procedure with the current estimates P1 and Q1. The elements of array B are obtained using the following recurrence relationship. Along with P and Q, B1 uses A1, B0, B sub minus 1, which yields 0.90 to 5057. Substituting A2, B1, B0, as well as P1 and Q1, gives minus 12.21027. B3 and B4 are calculated in the same manner, which yields 0.846216 for B3 and 0.907065 for B4. Next, we evaluate the array C. The starting values are 0 and 1. The C1 is obtained as follows. Likewise, we determine C2 and C3 to be minus 6.158261 and minus 15.23,976. The C bar 3 is obtained as follows. It is found as minus 16.08597. Now that we have the coefficients of the 2 by 2 linear system, we can solve the system for improvements, which leads to minus 0.091324 for delta P and 0.091256. The second step estimates can then be found as follows. We will skip the third iteration details. The third iteration yields smaller improvements, which in turn yield minus 2.299993 for P3 and 0.899995 for Q3. Note that the convergence criterion of absolute values of delta P and delta Q are yet to be satisfied. Repeating this iteration procedure one more time, we get the convergence criteria satisfied. P and Q values are found to be minus 2.3 and 0.9, for which the quadratic equation yields two real roots. We note that the last two elements of the array B, B3, and B4 go to 0. The prior three elements are also the coefficients of the quadratic equation. Whose solution also yields real roots, minus 4 and 3. The advantages of the method are: the Bairstow method is particularly efficient for finding both real and imaginary roots of polynomials, even those with high degrees. The method does not require arithmetic operations with imaginary numbers. The method does not require initial guesses for all roots, just for the two coefficients of the quadratic factors. It does not require partial derivatives. When the method converges, it converges with a quadratic rate of convergence. The disadvantages of the method are: the method is hard to understand and implement. It provides the roots of only polynomials. It requires a good set of initial guesses for P and Q. The closer the starting quadratic equation is to an actual one, the faster it converges. It is not suitable for every polynomial and has difficulty handling large polynomials. It can be sensitive to the initial guess and/or the coefficients of the polynomial. That is all for now. See you next time with another topic. Bye.